So hello and welcome student to this lecture, and this is course number MA412 linear algebra, and today we will discuss lecture number 32. Okay. Now recall in our last lecture we defined unitary operators and orthogonal operators. So these unitary operators are actually very special kind of operators. So why? So I will discuss that thing very soon. Before that, let us define one more definition. Okay. So when you talk about isomorphism on vector space, then we consider this is a bijective linear maps, right? But if a vector space has inner product, like the inner product space, then it is no longer the isomorphism on inner product space, because inner product space, the isomorphism should also satisfy that it preserves the inner product, right? So in general, it is not true that every vector space isomorphism on vector space is also inner product isomorphism. So what is the definition for that? So let V and W be two inner product spaces over the same field. Okay, so this is over F, same field F, and okay, maybe write it properly. Over F, some scalar field F, so a linear map, a map T belongs to LV, a linear map. Okay, or rather, I should not say LV, LVB. LVW. So the linear map from VW is said to be an isomorphism from V to V1 to whatever W, if what happens, if obviously it has to be bijective, and T is bijective, that is required for vector space isomorphism, and the most important property is that T should preserve the inner product. So there are, see, suppose you have inner product here, something, this one, inner product in W is inner product same 2, then T should preserve the inner product. What does that mean? So T preserve this inner product. So what does that mean? That means suppose you choose two vectors, say V1 and V2 in V, and suppose this is D1 inner product 1, and inside W, say inner product 2, and then the image TV1 and TV2, they should have the same inner product. Okay, this should preserve. Okay, so this type of maps are called isomorphism of inner product space. Okay, and now you recall the property what we discussed for unitary operators, that tells you that this is the inner product, right? So unitary operators are isomorphism isomorphisms of inner product spaces, right? It's obvious. Okay, and now obviously when you talk about unitary operators, so that means they also said that orthonormal basis to an orthonormal basis. So what does that mean? That means to be something, if we have two inner product space which is fine dimensional, then or rather yeah, so both are fine dimensional, then they are isomorphic if and only if they have the same dimension, right? Because if they have same dimension, then this inner product for first inner product space, the basis they will goes to the basis of the single inner product space, orthogonal basis, via this isomorphism, right? And that is true when the dimension is same. Now maybe I can give a proof for that. Okay, so let me just tell that thing. So maybe observation or what? Yeah, so proposition, maybe proposition. Okay, so let V and W be two finite dimensional space. V and W be two finite dimensional inner product spaces over the same field. Let's say something, say F. Okay, then we will say V is isomorphic to W. If and only if what happened, this dimension of V has to be equal to dimension of so one part is obvious. If V and W are isomorphic, then obviously the dimension is equal, right? So you need to prove the other way down. Okay, so okay, so how do I prove? So yes, proof. So one part is obvious, right? If V is equal to W, then dimension of V is actually equal to dimension of W, right? It's obvious, and this I am not proving. Okay, so conversely, let dimension of V equal to dimension of W. Okay, so so for example, fine dimension. So let me write down this n, and let us choose a orthonormal basis for V, because every fine dimensional inner product space has a orthonormal basis, right? So let say B equal to something like V1, V2, Vn, B and orthonormal basis of V. Okay, so you choose orthonormal basis of V, and you choose another orthonormal basis of W. For example, maybe say B1, and let me write down this is small w1, small w2, and small wn, because the dimension is same. B and orthonormal basis of W. Okay, they have the same dimension, so you choose two bases, and they are also finite. Then what should be the natural map? So the natural map, so define the basis going to basis, right? Define the natural map. So T from V to W by what? So T of this Vi goes to Wi, right? Small wi. So obviously, you remember the theorem that proves that if same basis to basis, then that will be one. That will be one linear maps. But this is not only so. So T is linear. Obviously, T is linear and bijective. Bijective is obvious because T is onto, it sends every basis element here, and on final vector space onto implies 1 on, right? So T is bijective, but it has one more property, because it sends this map is a linear map, it is bijective map, but it is actually sending one orthogonal basis to another orthogonal basis, right? So what does that mean? That means I should say that T preserved is a orthonormal basis. Orthonormal basis, right? So what does that mean? So it sends orthogonal basis to another orthogonal basis, and hence that it tells that we actually preserve the inner product. So what does that mean? That means if we choose some x y belongs to V, and you see that their image tx ty, they will be the same, I mean with respect to inner product in V and W, right? So for all x y belongs to V. Okay, so P preserve that thing. So what does that mean? That means T is a linear map which is bijective and which also preserves the inner product, because if something preserves orthogonal basis to another basis, they necessarily they preserve this thing, right? Because you can write down any x and y vector in terms of linear combination of the orthogonal basis v1, v2, vn, and then use the property linearity of first argument and conjugate linearity of second argument of the inner product, and it is clear that they will be same, right? So on finite vector space, inner product space, this is isomorphism gives you whenever they have the same dimension. This is obvious, right? Maybe let me just give some more example here. Okay, so maybe so example. Okay, so now so the standard, so you start with any inner product space B such a dimension of V equal to n, then obviously and V is over F, then obviously W, if you choose Fn, that F is the underlying field, they are isomorphic, that V has to be isomorphic to Fn, right, by any dimension, and that is obvious because you choose any orthogonal basis here. So inside V you choose orthogonal basis, say V1, V2, Vn, and inside Fn you already have a standard orthogonal basis, right? Say E1, E2, E1, E2, and En, right? So E1 is that vector where the only one ith coordinate is 1, otherwise 0. Similarly, Ei is the ith coordinate is 1, all the other coordinates are 0, right? And then you send this basis to basis. So that will be the isomorphism between these, right? This is standard example. Now let us give some interesting example. Okay, so maybe example 2. So for example, suppose you have say M33 over say R, for example. Okay, now you see that this is my obviously vector space. You can obviously define a product. I remember we did it. There is something called Frobenius inner product, right? But similarly, you can define inner product on subspaces of this vector space. There might be defined inner product, obviously. So now let me define this V. You can write down V1 plus V2, right? Where V1 is that symmetric space of symmetric matrices. So symmetric matrices space of and V2 is the skew symmetric matrices. So I'm taking over R real. Now so it is easy to see that so dimension of V is 9 here, right? I can easily find out the dimension of V1 is actually 6 and dimension of V2 equal to 3 actually, okay, because this is direct sum, right? And obviously these V1 and V2 are not any ordinary subspaces, they are actually eigenspaces corresponding to the map. This was a part of our exam question. So if we send the map T from V to V such that T of A goes to A transpose, then you can easily say that this map has actually two eigenvalues, and these eigenvalues are plus 1 minus 1, and V1 is the eigenspace corresponding to eigenvalue plus 1, V2 is the eigenspace corresponding to minus 1, right? So they are very special kind of subspaces. So now question is that because V3 is dimension 3 and I know a standard vector space of dimension 3 which is R3, right? So W is equal to say R3, which is dimension 3 also, right? So the theorem whatever we proved so far that whenever you have to find an inner space, if the dimension is same, then they must have isomorphism, right? Now question is that do you know any map from, for example, a map from say R3 to say V2 such that, this is question, such that T is an inner product isomorphism, inner product isomorphism. Okay, so this is another question to ask, and now let me just, obviously one can first ask me what is the inner product inside V2. Okay, so V2 so in V2 I am giving the inner product by this, so define okay, so maybe define inner product on this space of Q matrices by what? So you define you choose two matrices, say A and B, and V2 is a skew symmetric, right? And then you define this is half of trace of A B transpose. Okay, in general you remember the Frobenius matrix. So Frobenius, so you can define inner product for any kind of matrices, and for that we define by that conjugate transpose. What is that? Adjoint. So we choose A and B, and we define B star A, right? In a trace of B star A. But that is a general inner product for on any space of matrices, right? But because this is Q symmetric special type matrices, if you define this, you can easily check that this will be forms the inner product. So this this is homework, forms an inner product on V2. Okay, we can easily show that. Okay, and so obviously B transpose is nothing but Q symmetric matrix, means this is nothing but minus B, because this is real Q symmetric matrix, right? So it is actually minus of trace of AB, and this is actually the definition, right? So you can write down that minus of or rather so minus B, so that you can take outside obviously, and then minus okay, let me just write down by this, let us not, okay, then this is enough to define the inner product. Okay, now the question what I ask here, that because V2 and R3 have the same dimension, do we have a map which is actually isomorphism between inner product spaces R3 and V2, and R3 I am taking with standard inner product, and V2 I am taking the inner product defined by this operation. Okay, now how do you define such maps? Okay, so what does that mean? That means this is what we prove. We prove that you choose standard order basis, and then you send it to actually you choose for two vector space V and W, you take the orthogonal basis of V and orthogonal basis of W and send it to one by one. The same thing I will do here. So for R3, what is W here? So R3. So for R3, what will be my orthogonal basis? Say V1. So I can choose obviously E1, E2, E3. Okay, and for V2 over R, obviously what I'm choosing the basis, orthogonal basis. And what are the orthogonal basis here? So so 3 crossing matrix, right? So obviously exclusion matrix means diagonal has to be 0, and then you choose here 0 here and 0 here, and then put -1 here, +1 here, 0 here, 0 here. Now see, this will be a 1 skew matrix, and then another one will be 0 0 and say 1 0 0 0 -1 0 0. Okay, and then another one will be say 0 -1 1 0 0 0 and 0 0 0. Now you see that this will form, so this V2 is an orthonormal basis of V2, and this you can easily prove because just let me give the proof quickly. So so first of all, so what is the inner product with these two? This is maybe write down this may be alpha 1, alpha 2 and alpha 3 name, or maybe A1, A2, A3, A1, A2, A3. Okay, now what is the inner product of A1 with A2? This is half of trace of the matrix A and A1, A2 transpose, right? Now you just check it, it's immediate. So what is A1 is this matrix, so this is 0 0 1 0 0 0 sorry 0 0 0, this is 1 0 -1 0. This was is A1, and A2 transpose is what? A2 transpose is nothing but yeah, so it's nothing but 0 0 1 and 0 -1 0 0 0 0. Okay, now you take that product of these two matrices, and then you see that there has to be 0. So this is 0. Obviously now you can find out 0 0 0, and then this is this. And this is also 0 0 -1 and then 0 0 0. This is -1, obviously, sorry, 0 0 0 here, and then this one is 0, and the last one is what? Last one is 0, and then this is 0, and this is 0, right? Whatever. So the trace is always 0, so this is 0 actually. Similarly, you can find out that A1 A3 is 0 and A2 A3 is 0, and not only that, now you can understand why I choose half here. Now you find out what is inner product of A1 A2, then you will understand A1 A1. A1. So A1 is nothing but half of trace A transpose, right? Now half of trace of the same matrix with transpose. So you have 0, 0, 0, 0, 1, is 0, 0, 1, 0 minus 1, 0, and then transpose will be what? It will be nothing but 0, 0, 0, 0, 0 minus 1, 0, 1, 0, right? Now what is the product? Trace of, so this into this 0, this into this 0, and then 0, okay, and then this into this 0, this into this, and 1 minute. So this is okay, but this into this 0, this into this minus 1 plus 1, and this into this 0. Similarly, this into this 0, this into this 0, and this into this plus 1, right? Now what is the trace? Now trace of this matrix is 2. That's why we put half here to make this is 1, right? So that we can normalize that thing that in a product with AI with AI is always 1. Similarly, A2 is also 1, and A3 carry on. So that's why we put the half. Otherwise, if you don't put the half, then it will be only an orthogonal basis, not the orthonormal. Okay. Now the way we define that orthonormal basis goes to orthogonal basis, that will give the linear isomorphism between two inner product space, right? Then what will be the map? So you send E1 to A1, E2 to A2, and E3 to A3, and then done. Then what will be the map? So now you send yes. So now you define T of EI equal to AI. Okay, I equal to 1, 2, 3. Then you see that obviously the theorem we just proved before tells you that T is an isomorphism, right? Isomorphism in a product space. So what will be the general map? Then you write down V1, V2, V3 in R3, and then the image will be what? Image will be is in terms of this, right? So it will be so V1 going to A1, right? So A1 into V1, so A1 will be coming here. So okay, so let me just put 0, 0, 0, and A1 will come through this V1, this is minus V1, and this V2 and yeah, so this is minus V2 and V2, and then here you have V3 and minus V3. This will be the map from R3 to V2. Obviously this is a skew symmetry matrix, you can easily understand. Okay, so this is one example. There are obviously plenty of examples one can give, and this chapter tells you about that when two inner product space are isomorphic, then you need something more than linear maps or bijective linear maps. You need something called unitary maps. Okay, so unitary maps are the isomorphism of inner product spaces that is more than a vector space actually. I mean it's something more. Okay. Now okay, so now come back to what we are discussing, orthonormality. So you can define orthonormality for matrices also, the way we define for orthonormality and unitary, both things for matrices, and same thing we define for linear maps. Similar thing can define for orthonormal matrix also, right? So how do we define? So let me just write down. So square matrix, say A is called and orthonormal orthonormal. I mean, so this is for real square matrix I am talking about. Okay, I mean, rather for real both are same, so it's called orthonormal. And okay, so orthonormal matrix if obviously A transpose and A transpose A, they have to be same, which is identity matrix, and it is A is called unitary if what happen if A star equal to A star A equal to identity, right? Now for real matrix and real square matrix, unitary and orthonormal are same, but for complex it is not same. For complex, orthogonal and unitary are not same actually. Okay, so this is you have to remember. Okay, so now what happens if two matrices are say unitary? Then you can say actually something. You can say that if two matrices are unitary, then they are row. See, so okay. Before that, let us recall that if you start with a matrix which is non-singular, I mean determinant is non-zero, then what you can say that. So maybe just a remark I should say. If A is a non-singular matrix, then rows of A forms a so non-singular say n cross n matrix maybe, okay, forms a basis of Fn. F may be the field, real number or complex number, doesn't matter. Okay, so rows, similarly columns also, but I'm just focusing on rows now. They will form a basis, means the rows are actually linearly independent vectors in Fn, right? Now the question is that what happens if I have a orthonormal or rather unitary matrix. So if A star equal to A star A, so that is unitary case, then what happens? Then this is okay, so unitary, then the rows actually, the rows of A, they will form and not only basis, they will form an orthonormal basis, actually something more, because you have more condition here. Okay, orthonormal basis of Fn. Okay, now how do we prove this thing? So this is the proof is also simple, but let me just give you the proof. So suppose it is given that A equal to say Ij, okay, the matrix, and you want to know the rows are actually whether they are orthonormal basis or not. So what do you do? So you just take the matrix A and A star, and then you multiply them, and you check what happens. So if you multiply A and A star, then what happens? Rows of A and in A star, that is multiplied by column, right? But columns or A star are actually nothing but the conjugate transpose of rows of A, right? So you can write down that this matrix A star, and check what is the ith row and jth column element. So this is actually multiplied by that conjugate transpose of the rows of A or real matrix A, right? So on the one hand, because this is identity, A is identity, so this is identity, right? identity matrix, right? The ijth component of identity matrix, which is 1. So this is actually delta ij. When I is equal to j, it is 1, otherwise 0. On the other hand, by definition, this will be a, say, ik, and a star, let me write down, a star is nothing but conjugate transpose. So this is a star of kj, and k is running from 1 to n, right? This is the matrix multiplication. Now a star of kj is nothing but what? Nothing but a bar jk, right? This is nothing but summation k equal to 1 to n a ik and a bar jk, right? So this is exactly what I just was telling, that this is multiplication by rows of a with the transpose, right? Yeah, so sorry, but conjugate bar. Okay, so that tells you that they are actually forming orthogonal basis whenever j equal to k. So when so delta ij equal to this, and when delta I equal to, so if I equal to j, then what happens? Then this sum will be k equal to 1 to n a ik and a ik bar. This is nothing but 1, but this is what? This is actually summation a ik more ik whole square equal to 1 to n, right? Equal to 1. And this exactly gives you that the norm is 1 when you take that this standard inner product with respect to the fn, right? And when if you choose j not equal to I, and then this is actually 0, right? So what does that mean? That means they forms, actually the rows forms a orthogonal basis of fn. Okay, this is an important observation. What for starting with a non-zero matrices, where the rows or the column, whatever, they will gives you a only ordinary basis, not orthogonal basis, right? But here for unitary matrix, they will gives you orthogonal basis. Okay, so now we will define one definition, and then we will discuss one very important observation. Definition. Okay, so definition, let us define it. So suppose we have two matrices A and B, and then we will say that these two matrices are actually unitarily equivalent to each other. Okay, so let A and B be two matrices. We say A is unitarily equivalent to B if there exists a unitary matrix. Okay, so okay, so let me just define it, then I will tell you same thing you can do for orthogonal also. There exists an unitary matrix, say P, such that you can write down that A is actually P star, that adjoint conjugate transpose of P with B and P. Then we say that A and B are unitarily equivalent. Now instead of unitary, you can also change it by orthogonal equivalent. In that case, instead of unitary matrix, you have to change it by orthogonal matrix. Okay, orthogonal go null, and you have to change. In that case, you have to say that A equal to P transpose BP. Okay, so unitary equivalent means two matrices actually they are similar. And not only that, they are something called unitarily similar to one another matrix, right? You can convert from one matrix by another matrix in terms of a unitary matrix. Okay, now why this is important? Because it will gives you the classification theorem that what we discussed, I think, one or two lecture before, that whenever normal matrix is there and or other diagonal matrices are there, then it may not be normal always. So you can always say that if it is unitarily diagonalizable, means what does that mean? That means that you can diagonal one matrix, you can change one matrix to a diagonal matrix unitarily. So if there is a unitary matrix, then only you can say that the matrix A is actually a normal matrix. Okay, so I will give a proof obviously here. Let me just start with this theorem first. So let A belongs to, say, n cross n over C complex matrix. Okay, see, for real number, real matrix, you can do the same theorem, okay, for orthogonal equivalent, but I am doing for complex. Same thing you can do for real field also. Okay, so suppose you have a matrix which is n cross n matrix over C, then A is normal. This is very important theorem what I was just telling. A is normal if and only if A is unitarily equivalent to B. Okay, or rather, sorry, unitarily equivalent to a diagonal matrix, not B. B is the diagonal matrix. Okay, so in that example, you need unitary property. Okay, now this is if and only if condition. So what does that mean? That means if you start with a normal matrix, then you can find out the unitary matrix such that you can write down A equal to P star dP, where D is a diagonal matrix, and conversely. Okay, and conversely means if you start with a matrix A which is unitarily equivalent diagonal matrix, then you can also prove the A is normal. Okay, so for this proof, so let me just assume first that, so let let A be a normal matrix. Okay, now the moment you have a normal matrix, then you know that there exists a orthogonal basis consisting of, let me just write down that we already proved many times. And then there exists orthogonal basis, or rather an orthonormal basis, say B of Fn. Fn is that the n-dimensional vector space over F, right? So consisting of, so these matrices are nothing but, why I'm saying Fn, because this is n cross n matrix, right? So A can be think of a map from Fn to Fn. So let me write down there. So you can write down F from Fn, or yeah, so maybe in this case Cn, but write down in general Fn. So in this case F equal to C. Okay, so A is a map from Cn to Cn, or rather Fn to Fn. So this is unitary means you can find out the basis of Fn which is orthonormal, and it contains eigenvectors of A, right? So you can write down that some basis of this consisting of eigenvectors of A, right? This is clear. So that is the theorem you proved using Source theorem, right? Now once we have a basis which consists of eigenvectors of A, that means the matrix or the map that must be diagonalizable, right? So thus A is diagonalizable, right? This is obvious. Okay, so A is diagonalizable. So what does that mean? That means you can find out the matrix Q whose columns are the actually vectors of B, right? So thus there exists Q actually element of this N equals NC such that what happened? The columns of Q are actually they are actually the vector from the basis B, right? Such that columns of or rather I think there is no O here. Or this Q are actually this okay, so let me write down here this basis B. So B I can write down of the form some V1, V2, Vn, and the matrix my Q are actually columns are this V1, V2, Vn. These are n columns of the matrix, and obviously with the fact that if you write down Q inverse into A into Q, this will give you a diagonal matrix D, right? This is D diagonal. Okay, now once you have once you have D which is such that D equal to Q inverse AD, then you can say that A is actually similar to a diagonal matrix. But I need to prove something more. I need to prove that A is unitarily equivalent. So what does that mean? A is similar to unitarily similar or equivalent or unitarily similar to D, right? So I need to prove that the matrix Q is also unitary. Now how to prove EQ is unitary? Because all the vectors columns are A are actually orthogonal basis. So what does that mean? That means so this observation tells you that Q. Okay, so this Q inverse AQ equal to this, and now you see that what is Q star in this case? Q star will be what? So Q star will be actually because this B1, B2, Vn these are orthonormal basis, so Q star will be nothing but Q inverse actually. Okay, and this will gives you that yeah. So I need to prove this is a unitary matrix. What does that mean? That means I need to prove that Q and Q star they has to be identity, that is true here, and also Q star Q is identity, that is true because Q star equal to Q inverse, right? And hence you can say that D is actually Q star A Q, and hence that's the condition that A is unitarily similar or equivalent to the diagonal matrix, right? So this is the one part, and the converse part is also very easy. So conversely, let A is unitarily equivalent to a diagonal matrix say D. So what does that mean? That means there exists a Q. So Q is unitary such that whatever has a D will be equal to A star, Q star A Q, right? Okay. Now to prove that Q is normal, what do you need to prove? You need to prove that Q commutes with Q star, but that is obvious. A commutes with A star. But so what is A then? So yeah. So you just multiply. So this is Q inverse, right? So this is Q D. You just multiply by Q, A star equal to Q inverse, and then you multiply by Q star, which is A, and you just put the value here. So A equal to Q D Q star, and also Q D Q star whole star, right? So what does that mean? That means this is Q D Q star, and then Q count D star and Q star. But Q star Q equal to identity, so you will have Q D D star Q star, right? But you know the diagonal matrix commutes to each other, so this D star is nothing but D star D, so you can write down the Q D star D Q star, right? So so now you can do one thing. You can input. So what was your Q? Your Q equal to Q D Q star, so you can write it down as Q D star Q star, and then Q D Q star. This identity, put it. Now issue, this is what? So this is actually A star. 1 minute. I think there's an issue with star. So yeah. So this is and there's issue with star. You can, I think you should start with star here, and this is different. This is obvious because if Q unitary, you put Q star equal to P, then it is done. Okay, so you just put here star, then it will be easy. You remove here. Okay, remove from here, and now you put here. This is star here. Okay, Q star here. Now Q star here, Q star here. Remove from here. Yes. So again, star. So this is star. This is Q, and maybe let us not bother about it. So you just remove full thing here and do it here again newly. Now you find out. So this is your A star. Now you do A star A. Now what will A star A? So A star A will be exactly. So this is your A star. Now A star A, you just do again thing, and then you will have exactly Q star D star dq. Okay, so these two commutes actually, so this will gives you that A is normal. A is normal. Okay, so what does that mean? That means a complex symmetric square matrix is normal if and only with unitarily equivalent to a diagonal matrix. Similarly, for real symmetric square matrix, you can replace the normality by something called symmetric matrix, because in that case A equal to A star, A equal to, you replace that by symmetric matrix, means A equal to A transpose, and you can prove that the matrix is symmetric. So next theorem, the same similar theorem, similar proof. Just let me write down. So if you start with A in terms of say n cross n over R, real number, then what you can say? You can say that A is symmetric if and only if A is orthogonally equivalent to a diagonal matrix. And the proof is similar, because whenever you have a symmetric matrix, then obviously A equal to A is transpose. Okay, and so whenever you symmetric matrix, then you can, they are self-adjoint, right? So or rather Hermitian, whatever you say, real self-adjoint or Hermitian, and then you can use the fact that real vector space self-adjoint matrix, if and only you can find out a basis of that in a product space which is orthonormal, and this basis forms this basis contains the eigenvectors, right? So same proof will go through here also in case of real symmetric matrix. Okay, so maybe I will stop here, and this actually gives us the motivation towards this orthogonality and unitary operators quite well. Okay, so I'll stop here.